Something that can also be considered simple harmonic motion is a pendulum. Right, so if you have our pendulum that swings back and forth like this, we can also consider that simple harmonic motion. So remember, simple harmonic motion by definition has to obey Hooke's law. And so that means that my restoring force has to be proportional to my displacement. So let's take a look and see if we can figure out what the restoring force is. Right, so if we have kind of the center line of our pendulum here where it passes through the center, so our pendulum is going to swing this way and starts out at some angle there. Let's look at the forces acting on the pendulum right now. The most obvious force would be gravity, which acts straight down, right, always towards the surface. So there's force of gravity acting straight down on whatever mass is hanging off the end of this pendulum. And kind of like we did in our forces unit, we can split this up into an x and y direction. And so there would be maybe force of gravity in the y direction, and here would be force of gravity in the x direction. So what we can kind of see by this is that we have gravity in the y pointing this way, but force of gravity, notice where that's pointing? That's pointing back towards the center. And everywhere along this path, that would be the case, that force of gravity is always going to point back towards the center, always going to point back towards the center, until, okay, let's say for example now we're at this spot here. Once our pendulum is at the very center, now all of my gravity is in the y direction, so my force of gravity in the x, right at the center, is actually 0. Which, if you remember, is very similar to our sort of spring mass problem where we had our spring moving back and forth, and right in the very center our force was 0 and our acceleration was 0, but that's where we're moving the fastest. Very similar to our pendulum. So our restoring force in this case is equal to the gravity just in the x component. And if we remember something from our chapter on forces, we were dealing with angles and things like that, our force of gravity in the x direction would be mg sine theta. And to make it kind of consistent with what we know from Hooke's law, right, we could throw a negative sign in there saying that it's always acting back towards the center as well. So negative mg sine theta is our restoring force for a pendulum. So just like with our mass spring system, we had equations for period and for frequency, and so we'll do the same thing for a pendulum. So period for a pendulum is going to be equal to 2 pi square root of the two things that matter for a pendulum, just the length and the acceleration due to gravity at whatever location we're at. So 2 pi square root of L over G, remember G for Earth is going to be our 9.8 meters per second squared. And since frequency is equal to 1 over period, we're going to just flip everything around, 1 over 2 pi square root G over L. And those will be our two equations for a pendulum system. So both of these, good for pendulums. So anytime you're reading a problem with a pendulum, it's a good place to start. So let's do a quick sample problem with the pendulum. So we have a pendulum with a length of 75.000 centimeters and a period of 1.7357 seconds. And we want to know the acceleration of gravity at that location. Notice we're very precise on these numbers, right? Lots of decimal places carried out in our actual measurements. And so what this kind of tells you is that this is a really good way of determining gravity to a very precise value. And that's something that we can use pendulums for. It turns out that 9.8 that we use actually varies a little bit as you go across the Earth. Closer you are to the equator, the Earth actually bulges a little bit, so you're actually a little further away from the center, so you have a smaller value. And up near the poles, you'd have a bigger value. The 9.8 is just kind of an average for all over Earth. So let's see if we can figure this out. So we have period equals 2 pi square root of L over G, and there's our equation. So our period, 1.7357 seconds, equals 2 pi times the square root of 75.000 centimeters over G, and we're going to solve for G here. So first thing is divide by 2 pi, 1.7357 seconds over 2 pi equals the square root of 75.000 centimeters, except we should change that to meters, and so it would be 0.75000 meters over gravity. So we're going to square both sides. And this is where we have to be kind of careful with our algebra. This is probably the most common mistake I see. Is we would do 1.7357 squared. And then that squared also goes to both of these, so 4 pi squared. And then when you put that in your calculator, you want to make sure and have parentheses around that so that you're dividing by both the 4 and the pi squared. That's really the most common mistake I see all the time, is not putting parentheses around the 4 pi squared in your calculator. So 0.75000 meters over g. So we just need to solve for g. So we're going to multiply g to both sides and then divide 0.7500 by the quantity over on the left-hand side. And when we do that, we get 9.8281 meters per second squared. And that would be our final answer. And notice, because we were very precise with our numbers up here, right, because it's clear from our numbers that we measured to a good degree of accuracy, we can kind of carry out our number to a couple extra digits over here, and we can see, 9.8281, so there's that little extra past the 9.8 that we usually use, and that's where you're going to see the variation with gravity.